Hello, everyone. I'm Yawen Wang from Stanford University. Today, I will talk about SOL, Safe On-Node Learning in Cloud Platforms. This is joint work done among Stanford University, Microsoft Research, and University of Texas. For my talk today, I'll first describe the advantages of using on-node machine learning for server management in the cloud. I'll then show the findings from our study of 77 Azure node agents and how on-node ML can benefit them. Next, I'll describe the challenges in deploying on-node ML-based agents in production and present our solution, SOL, the Safe On-Node Learning Framework that helps build agents to operate safely in production. I'll discuss the key design insights behind SOL and also how to develop agents using the SOL API and runtime. I'll conclude the talk with evaluation results of the on-node learning agents we developed in SOL. Today's cloud platforms consist of millions of heterogeneous servers. One approach to help better manage this complicated cloud of servers is to leverage on-node machine learning, where both the training and inference happen on each server node. Prior works have demonstrated the benefits of incorporating ML logic into on-node management agents. The table below summarizes a few of them, where on-node ML were shown to help substantially improve server utilization or performance. On-node learning has several inherent advantages. With on-node ML, we can get fresh workload-tuned models and predictions that can quickly reflect changes in workload patterns, whereas off-node training or inference would not be fast enough to capture these changes. Furthermore, on-node ML allows the model to access fine-grained data telemetry to learn high-frequency workload dynamics. This data would otherwise be too expensive to shape off the node. To help better understand what kinds of software agents run in production servers and how on-node ML can benefit them, we surveyed existing node agents that run in Azure today and found that there are 77 different node agents. Based on the tasks they perform, they can be grouped into 7 categories, including server configuration agents that configure nodes' hardware and software, long-running service agents for services like VM creation and migration, monitoring and logging agents that monitor various CPU counters and network telemetry, watchdog agents that watch for problems or errors, resource control agents that manage resource assignment, and also access agents that grant operator access to the server. Based on what they do, these agents run at different frequency, on the order of seconds to months. We identified that agents that collect data to make frequent decisions based on current environment and workload are good candidates for leveraging on-node ML. And this type of agents fall under the categories of monitoring, watchdog, and resource control. For monitoring agents, they can use on-node ML to dynamically select optimal sampling frequency to minimize monitoring cost. For watchdog agents, they can learn from node data to detect problems and take actions earlier. And resource control agents can learn from workload dynamics to improve node utilization and performance. Let's now look at a more concrete use case of on-node machine learning. We have developed this agent called SmartOverclock. It leverages Q-learning to dynamically overclock CPU. The goal of this agent is to maximize workload performance while not wasting power. It collects data telemetry and changes CPU frequency every 1 second. This diagram shows the general workflow of the SmartOverclock agent. It starts by collecting data about instructions executed per second. It then updates the model by computing a reward and update the Q table. Its model learns to overclock if overclocking leads to consistently higher IPS for the workload. After the model is updated, the agent selects the optimal CPU frequency using the Q-learning policy. Then it sets the CPU to the selected frequency. And finally, it loops back to collect new data again. We observed that this workflow is common across different learning-based on-node agents. Despite the many benefits of on-node ML, it remains challenging to be deployed in production. The first challenge is that agents could read bad input data that causes models to be trained incorrectly. For example, the overclock agent could read invalid data from corrupted CPU counters. This plot shows that with 25% invalid data passed into the SmartOverclock model, the performance of the agent can degrade significantly by more than 80%. To avoid this problem, data assumptions should be explicitly checked and enforced during the run of the agent. Secondly, the model itself could exhibit poor accuracy. It could be a miscalibrated model, or the workload itself is unlearnable. To address this, the agent should continuously evaluate model accuracy while it's running and avoid using predictions from an inaccurate model. The next challenge comes from unpredictable compute availability. This is because on-node learning agents are co-located with customer workloads on the server. Since customer workloads have top priority over server resources, on-node agents can be blocked from running for an arbitrary amount of time, leading to stale predictions that are no longer applicable. To address this challenge, the agent should account for stale data or predictions when it's running. The last challenge is maintaining overall performance and reliability of the server node. For example, the SmartOverclock agent could perform too much unnecessary overclocking and waste power. Therefore, on-node learning agents should monitor overall server state and support restoring the server node to a safe state when problems are detected. In an attempt to address all these challenges, we propose SOL, a general safe on-node learning framework that helps develop and operate ML-based agents to be robust under a variety of failure conditions from production. When designing SOL, we leveraged a few key insights. The first insight is that node agents are heterogeneous. They read different counters, perform different tasks, and operate at different timescales. All this logic is agent-specific. However, agent structure and failure conditions are shared across on-node learning agents. This includes the ML-based control operations and also the types of problems they could encounter when deployed in production. SOL leverages these commonalities to provide a simple API and runtime to help develop safe on-node learning agents. Let's next delve deeper into the design of SOL. First, SOL identifies these four operations: collect data, update model, model predict, and take action, to be common across on-node learning agents and abstract them out. Next, SOL decouples actuation logic from the ML logic, splitting them into the model and the actuator. The model and the actuator run in separate threads, and the model communicates with the actuator through a prediction queue. If the actuator does not receive a prediction in time from the model, instead of relying on a stale prediction, it can fall back to a default action as specified by the agent developer. Now the actuator won't be blocked by delays from the model, which is more likely to happen because the model thread carries out more compute-intensive work. Lastly, SOL integrates Watchdog-Style safeguards to automatically detect and mitigate problems when agents are deployed in production. The first safeguard added is the data validation safeguard. Now data collected will be validated first, and only valid data will be passed into the model. Next, a model safeguard is added to assess model accuracy. If the model passes the accuracy threshold, the prediction from the model will be used. If not, a default prediction is used instead. A safeguard is also added to the actuator to assess the overall agent performance. If the check is passed, the actuator takes an action based on the model prediction. Otherwise, it takes a developer-specified safe action instead. To help guide agent developers in building safe learning-based agents, SOL presents a simple API, including the ML-based control operations and Watchdog-Style safeguards that I discussed in the previous slides. The API function names are shown in the diagram below. To develop a new agent in SOL, agent developers just need to provide implementations for this API function signatures, depending on the agent-specific logic. To run a SOL agent, all agent developers have to do is to first specify parameters for how often agent functions need to be run. Then implement the model and actuator interface. And lastly, pass them as input into the SOL runtime. The SOL runtime will then be responsible for scheduling and executing various agent functions. For the experiment setup, we run all the experiments on a single server node, running the Hyper-V hypervisor. The SOL agents run in user space, and the SOL runtime runs in the same process as the agent, as shown in this diagram below. Different failure conditions are injected while the agents are running to evaluate how robust the agents are to different problems. For evaluation, we implemented 3 different on-node resource management agents using SOL. The SmartOverclock agent manages CPU overclocking to improve workload performance while not wasting power. The Smart Harvest agent manages CPU scheduling to improve CPU utilization while not impacting customer workloads. The Smart Memory agent manages memory migration to reduce memory page scanning cost while still accurately detecting memory pages that are cold. These 3 agents we implemented are considerably different from one another. They differ in the type of resources they manage, the input data and ML models they use, as well as the timescales they run at. For this talk, I'll focus on discussing experiment results for the SmartOverclock agent. However, you can find more detailed evaluation for the other 2 agents in our paper. To evaluate SmartOverclock, we try to answer the following questions. First, how does SmartOverclock compare with other static policies? And after establishing the usefulness of on-node learning, we try to answer the following questions on how effective SOL is in mitigating impact from various issues that could occur in production, including invalid data, delayed prediction, inaccurate model, and idle server. For SmartOverclock, we compare it with static policies at fixed frequencies of 1.5, 1.9, and 2.3 GHz, where 1.5 GHz is the nominal frequency. The SmartOverclock agent can dynamically choose among these 3 frequencies. The top plot shows the workload performance and the bottom plot shows the power usage, both normalized to the values of the workload when it is run at the nominal frequency setting. The first workload is a synthetic workload that processes periodic batch jobs. SmartOverclock achieves close performance to the highest frequency setting while reducing power by more than half. Note that SmartOverclock does not achieve highest performance because it employs a 10% random exploration to detect for any changes in workload patterns. The second workload is object store, a key value server running at high load. This workload always benefits from overclocking, and SmartOverclock learns to overclock for it, achieving similar performance as the highest frequency setting. The third workload, disk speed, is a disk-bound workload that does not benefit from overclocking, and SmartOverclock correctly learns not to overclock for this workload. This set of results show that the SmartOverclock agent can achieve near optimal performance and power usage on a variety of workload patterns. Next, we try to inject invalid data into the SmartOverclock agent by returning random out-of-range IPS data. This plot shows the power on the y-axis and workload performance on the x-axis, both normalized to the results of the agent when it's run under the ideal setting, without any invalid data. We can see that even 5% invalid data can lead to a significant drop in agent performance. And as we add more invalid data, the agent continues to perform worse. However, once we add a data validation safeguard as required by SOL, the safeguard validates the data before consuming them and drops any out-of-range data, thus successfully preserving the model accuracy, as shown by the yellow circle on this plot. And this pattern is observed across different percentage of invalid data. Next, I'll show the results for delay prediction, where a delay is injected in the model thread during a workload phase change. In this plot, the blue dashed line shows the CPU utilization of the workload. For the synthetic workload, overclocking is beneficial when CPU utilization is at 100%, when all cores are busy processing the batch job. A 30-second delay is injected in the model thread when the workload finishes processing a batch. A blocking actuator would always wait until a prediction is available from the model, so it will be impacted by this delay. Continue to unnecessarily overclock CPU when the new prediction is delayed. This can create a 36% increase in power usage. On the other hand, with the non-blocking actuator design in SO, the agent can restore the node to a safe state at the nominal frequency after a 5-second wait on model prediction, hence reducing power usage dramatically. Due to the limited time, I won't be able to go over the complete set of evaluation results for SmartOverclock, so I invite you to read more about them in our paper. In conclusion, we present SO for developing safe on-node learning agents. SO is a general and extensible framework. It facilitates development and operation of safe agents under a wide range of realistic issues in production, including bad data, inaccurate model, scheduling delays, and impact on node performance and reliability. We also implemented 3 agents in SO and show that ML-based resource management agents have great potential, and also SO can help build them to safely operate under different failure conditions in production. Thank you for your attention, and please let me know if you have any questions or comments.